শেয়ার করে দেন লিংক করো।
So the definition of vector space, let V be a set where V contains element x, y, z. So anybody can. So লাইভ হচ্ছে না, এই লাইভ হচ্ছে না। So let V be a set where V equal to the elements of V are x, y, z, etc. So V is strict like V plus, this is a vector addition, and star, this is scalar multiplication, is called vector space over R. Here I can consider R instead of field, but this is also true for any field F. But our purpose, I only consider R. I restrict here, it is R. So V plus star is called vector space over R if it satisfies following axioms. One,
What does V know? What does V know?
V is a set. V is a set, any set. Okay.
Before the vector addition.
So and this is called vector addition. I define it. This is a vector addition. And this is a scalar multiplication. Okay, Bishari? Okay. So this is V is a set, and this triploid means V vector addition plus symbol and star is called vector space over R if it satisfies following axioms: V cross V to V, that is, if we take any two elements xy which belonging to V, then x y will generate x plus y. This is also, if this also belonging to V, this is called closure property, that is V is closed under vector addition. So, for example, suppose I take V equal to R square. So this is a collection of xy such that x comma y belonging to R. That means any point in two-dimensional space. So now I define this addition, this is a function, as is belonging to V. I denote this x curve and y curve is belonging to V. Then if I define addition as then you see that this element also belonging to R and this is also belonging to R. So again a new element, this also belonging to R square. So this V flows under vector addition, and if you define another way, say the second element is 0, then again you see that it's also belonging to R square. So again, if you define addition as follow, then again it is closed under vector addition. Next, scalar multiplication. I define a function scalar multiplication as follows. Take two elements where alpha belonging to R and y is belonging to V, then we get element alpha y. If this alpha y belonging to V, then we say that V is closed under scalar multiplication. This V is closed under scalar multiplication. So V plus star is called vector space if it satisfies. First one is closed under vector addition. Second one is closed under scalar multiplication. Next, third, so there are so many examples where this is not closed under addition. For example, take V is a set of natural number. Okay. Now, set of natural number. Sorry, you take V is set of set of okay, natural number, no problem. And suppose I define addition as natural number means 1, 2, 3, 4, etc. Define addition as x plus y is nothing but a x minus y in that way. So addition is a function. So if you take x is equal to 1 and y equal to 2, then you see that this is x plus y. I think it is better to write in that way. Fxy, this function I define x minus y, then you see that your fxy is minus 1. This does not belong into system. Hence, this is not closed under addition. Okay. So, Rishiraj, clear or not? All set doesn't mean the set closed under. Okay. Okay. Thank you. Thank you. Thank you. So this is a function. You don't think like a x plus just like a addition 1 plus 2 equal to 3. This is not a 1 plus 2 equal to 3. This is a function, simply a function. I define this addition function as x minus y. Then you see that this does not close under addition. Okay. So the first thing is closed under vector addition. Second axiom is closed under scalar multiplication. Third, this is a associative property. This is an associative property. So x plus y plus z equal to x plus y plus z. This is true. If this is true for all x, y, z in V, this is called associative property. Associative property. Next. axiom. There exists theta. This is null limit. There exists theta such that x plus theta equal to x for all x belonging to V. This theta is called null limit. Next, there exists minus x. Belonging to V such that x plus minus x equal to theta for all x belonging to V. This is called additive inverse. Fourth point, okay. Fourth point is theta. This is null limit. For example, take V equal to R square. So the element of V is any point into two-dimensional space. The null element is theta is 0, 0. So if you add, if you define addition, first you define your addition. As follows. Then zero, if you add this, then you get, see, this is a real number, x1 plus 0, so you get x1, x2 plus 0, x2. So null element means that if V is a vector space, then there exists element. There exists element such that if you add this element with any element of this V, then you get the same element. Then this element is called theta. So null element not always exist. For example, if you define your addition as then you see that if you consider 0, 0 as a null element, then you see that x1 plus 0, according to this definition, this is x1, but your second element x2 plus 0 should be 0. Because you define your addition as follow. So this x1 comma 0 is not x1 x2. So if you define your addition as follow, then in that situation null element does not exist. So for vector space, null element is, there is a null element in V. So, are you understand, Swarnapu? What point? Okay, I think Swarnap, are you there? Okay, I think you clear what is the what do you mean by null limit. So so fifth point is the additive inverse. 6 point. Okay, thank you, thank you. One x equal to x for all x belonging to V. Then C plus xy, cx plus cy for all x comma y belonging to V, C belonging to R. This is called distributive property. Next point. C1 plus C2 x, C1 x, C2 x for all C1, C2 belonging to R, x belonging to V. C1, C2 x, C1, C2 x for all C1, C2 belonging to R, x belonging to V. So if V plus star satisfies all these 9 axioms, then you call this V plus star is a vector space over R. So I consider some example to illustrate these axioms. Example 1. Shani, what do you mean by should not? Should not satisfy what? Okay. Shani, Please complete your sentence. Okay, example. Suppose I take phi equal to r square, where then V contains element as follows. So this is nothing but any point in two-dimensional space. Now we define. Okay, sorry, this is correct. I forgot to mention one more property, that is property number 10, that is commutative. If x plus y equal to y plus x. Thank you, Vishali. For all xy, belonging to R. So all these 10 properties, the vector space satisfy all these 10 properties. Thank you, Vishali. You are right. I forgot to mention this is the commutative property. Okay. Thank you. So now I consider V equal to R squared. This is any point in two-dimensional space. Now I define addition where this x, I think it is better to write x card x2 x1 x2 belonging to R. This is x1, this is x2. Okay, so I write this x card as x1 x2, y card as y1 y2. I define addition as and scalar multiplication as okay. Now first I see that the new element after addition, that is x1 plus x2 0, this is also belonging to V because this is lies in this x-axis, any point in this x-axis. So this is a subset of V, so this is belonging to V, hence first property satisfied. So V is closed under vector addition. Next, this is again we see that if we define scalar multiplication as follows, second component is 0, then you see that this also lies in this line, this is the x-axis. So this is also belonging to V. So V is closed under scalar multiplication. Hence, property number 1 and property number 2 satisfies. If you define vector addition and scalar multiplication as follow, then you see that property 1, that is V is closed under vector addition and V is closed under scalar multiplication, property 2, these two properties are satisfied. Next, that is commutative property, property number 10, x curl plus y curl is given x1 x2 plus y1 y2. So x1 plus y1 0 and y curl plus x curl y1 plus x1 0. Since this is a real number is a field, so we know field satisfy commutative property under addition. So we write x1 plus y1 and hence x curl plus y curl equal to y curl plus x curl. Hence property 10, that is commutative property. It is better to write this is property 3, third property. This commutative property is satisfied. Now, fourth property, that is associativity. I take 3 elements, say x, x1, x2, y curl, y1, y2, z curl, z1, z2, then x curl plus y curl plus z curl, then so first you add these two parts. This give you y1 plus z1 0, then x1 plus y1 plus z1 0. Next, x plus y plus z. So first x curl plus y curl, this give x1 y1 0 plus z1 z2. So again you get x1 y1 plus z1 0. Hence associativity property hold. Third, next fifth, that is null element. Suppose if you take 0 0 as a theta, then you see that x curl theta, or we simply write 0 curl this is x1 x2 plus 0 0 equal to x1 plus 0 0, this is x1 0. This is not equal to x squared. Hence, null element does not exist. Next, inverse. If you take inverse of x squared is minus x squared, I write it as minus x1 minus x2, then you see that x squared plus minus x squared. So this is x1 plus minus x1 0, so 0 0. But this is not a null element, so here inverse, additive inverse does not exist. Next property, 1x. 1 is a scalar, so 1x curl is x1 0, because I define scalar multiplication as lambda x squared equal to lambda x1 0. So this is again not equal to x squared. Hence, this property, this axiom also does not hold. Next, C1 plus C2 x squared, this is equal to C1 plus C2 x1 0 equal to C1 x1 C2 x1 0 and C1 x squared C2 x squared, this is C1 x1 0 plus C2 x1 0, and this is equal to C1 x1 plus C2 x2 C2 x1 0. Hence, C1 C2 x squared equal to C1 x squared C2 x squared hold. That is distributive property holds. Next property, C x curl y curl. This is equal to C x1 plus y1 0. Then again C x1 y1 0. Repeat 0.7. That means this. Okay. I define scalar multiplication here. That is lambda x curl. This equal to lambda x1 0. Second component is 0. Okay. That is lambda x curl equal to lambda x1 0. Here your lambda equal to 1. Then 1 into x curl equal to 1 into x1 0. So x1 equal x1 comma 0. So x1 comma 0 is not equal to x curl provided x2 not equal to 0. Clear? Okay, thank you. So now C x curl, C y curl, C x1 0 plus this is C y1 0. So C x1 C y1 0. Hence this property also hold. I think this property number 9. And the last property, that is C1 C2 x curl. C1 C2 x curl means C2 x1 0, and this again C1 C2 x1 0 and C1 C2 x curl. This is C1 C2 x1 0. Hence this property also hold. So here if you defined vector addition as x1 y1 0 and scalar multiplication as, then you see that additive null element and additive inverse do not exist. Hence, in this situation, r square plus star is not vector space over R. So, if you define addition as follow and scalar multiplication as the following way, where second element is null, then you see that first this two will means this vector addition is closed under this V is closed under vector addition and this V is closed under scalar multiplication. If you take V is a R square, suppose if you take V equal to R square and that is R square V, then R square, and we define vector addition as follow and scalar multiplication R square R square, that is lambda x lambda x1 0, then we see that R squared is closed under vector addition and scalar multiplication. And also associative property holds. Even the property that is in null element, suppose your null element is 0 curl, theta equal to 0 curl, then you see that any vector, any elements in V, x1, x2, I denote this x curl, now x and take theta equal to 0, 0 null vector, that is in two-dimensional space. I take origin as a null element. So x curl plus 0 curl, that is x1, x2 plus 0, 0. Then according to these definitions of vector addition, we get x1 plus 0, x2 plus 0 equal to x1, x2, x curl. Hence, here null element, that is 0 curl, it is better to write theta curl. The null element theta exists, and theta is 0 curl. Okay, so I take null element theta equal to 0, 0. Then now, sir, we show that the non-existence of null limit, which shows that it is not a vector space already, but I define addition as follows: x1 plus y1, x2 plus y1. My previous example, I defined addition. I think I write addition as a function. This is x is nothing but a x1, x2. Y is nothing but a y1, y2, and these functions is defined as x1 plus y1, 0. If you define addition in that way, then you see that the null element does not exist. So, for this reason, r square plus this plus defined as follows, and start, this is not a vector space. Overall. Now I change this function, addition function, and now I define this addition as follows. X1, y1, and second component is x2 plus y2. Then you see that if you take null element as a origin, that is 0, 0, and then take any element x squared which belonging to r square, then Rishiraj, can you see this? Hello, Rishiraj. This is x squared. So if you define addition following way, then you see that your null element exists. So here, null element exists. Okay, thank you. Now, next, fourth point, that is fifth point, because first point is vector addition, closed under vector addition. Second point is Second axiom is closed under scalar multiplication. Third is commutativity property. Fourth is existence of null limit. And fifth axiom is existence of inverse element. Now, take x curve x1, x2, any point in two-dimensional space, and define minus x curve as now according to the definition of vector addition. So since these are the real number, x1, x2 are the real number, and since real number is a field under addition, so it should be 0. So this is a theta. Additive inverse exists. Hence, additive inverse exists. Now, sixth axiom. That is 1 into x. Recall the definition of scalar multiplication. Here I define scalar multiplication, that is lambda x third equal to lambda x1 0. So here is lambda equal to 1, then 1 into x1, second component is 0. So this is x1 comma 0. This is not equal to x card provided x2 not equal to 0. Hence, axiom number 6 does not hold. So, this is the problem. If you define scalar multiplication as follows. Even if you define your addition in conventional way, that is x1, y1, x2 plus y2, still this is not a vector space under this operation. Overall. So now if I define vector addition, first I take V as a R square, please wait. So if we define, first I take V equal to R square and define vector addition as follow. And scalar multiplication, then you see that all these 10 axioms are satisfied. In that situation, it should be because according to the definition, it should be lambda x2. So in that case, it should be x card. Hence, axiom 6 holds. Similarly, you can easily check that axiom 7, that is distributive property, C x card plus y card, C x card plus C y card, then C1 C2 x card and then property number 9, C1 C2 x card, C1 C2 x card. All these properties, all these axioms are satisfied. So if you define vector addition as follow and scalar multiplication as follow, only in that situation, V here is R square. Addition, vector addition, this is defined as follow. Scalar multiplication, this is defined as follow, is a vector space over So if you define your vector addition as follow and scalar multiplication as follow, in that situation, this is the only situation this R squared is a vector space of R. Similarly, for n-dimensional space, Rn, this is a Cartesian product of R in time. This is a collection of n-component vectors note that the elements of V, where V is a vector space, the element, note, the element of vector space is called vectors. So if V is a vector space, then its elements are called vectors. So if we define, now we take V equal to Rn, that is the n-dimensional points of n-dimensional collection of a points of n-dimensional vector space, and if you define vector addition, that is Rn I denote this n-component elements by x squared. So this is curve y curve. I define this vector as x1 plus y1, x2 plus y2, xn plus yn, and scalar multiplication then you see that this Rn plus star is a vector space over R. For this reason, we define our addition as follow, that is the element-wise addition, and scalar multiplication as follow. So under this condition, V is called under this condition, V is called vector space if V is closed under vector addition and and this vector addition means this, and scalar multiplication. So this definition holds only if we define our addition and scalar multiplication as well. Otherwise, this is not true. And moreover, I want to mention that I restrict our discussion only RE, because in our statistics we consider the points in n-dimensional space. Here, the following hold for all x current belonging to V. V is a vector space, and if I say V is a vector space, this implies V means V plus star is a vector space over R, which satisfies all 10 axioms which I already mentioned. The following hold for all x curve belonging to V and alpha belonging to R if the following hold for all x curve belonging to V and alpha belonging to R. 1, 0 x curve equal to alpha theta curve. Alpha theta, cannot see the second line of theorem. Okay. The following hold for all x. Now, Rishiraj, can you see this? Okay. For all x belonging to V and alpha belonging to R. Okay, thank you, thank you. Zero x alpha theta equal to theta. Theta is your null element. And if since V is your vector space, this is called null vector. Alpha x equal to theta imply alpha equal to 0 or x is equal to theta. Third, minus 1 x equal to minus x. Proof. First, this. Zero is a null element in R, where R is a field under addition. So this is equal to 0, can be written as a 0 plus 0 x. Now, I think 7th or 8th axioms of vector space, I forgot. This is a C1 plus, I use this axiom C1 plus C2 x distributive property. C1 plus C2 equal into x equal to C1 x plus C2 x. So I think it is 7th or 8th or 9th. I forgot this property. I think axioms. The number is 8th or 9th axioms. Please mention this thing here. So here 0 is C1 and C2 is 0. Then 0 into x plus 0 into x. So now we know if theta is a null element, then we know x for all x plus theta equal to x. If theta is null element, then you see that suppose 0 into x, this is a element belonging to V because V is closed under scalar multiplication. So 0 into x belonging to V. So suppose I write this as x star, which x star belongs to V plus, suppose this is again x star, or suppose I write this theta or x star, whatever that, and this is again x star. So if you compare this thing with that, then you see that 0x is equal to theta. All right. Okay. Thank you. Thank you. Eighth property. Eighth axiom. Okay. So if you compare with this, then you see that 0 into x equal to theta. All right. So this portion hold. Now alpha theta equal to alpha, since we know theta plus theta equal to theta, use this, put x is equal to theta, you get this thing. So I write alpha theta plus theta. Now we use, I think, 9th axioms. I use this axiom x c into x plus y equal to cx plus cy. Then alpha theta. Now compare with this, then you see that alpha theta equal to 0. Alpha theta equal to theta. Hence, 1 is proved. Now, next part, alpha x equal to theta given. Now we want to prove that this implies either alpha equal to 0 or x is equal to theta. That is null limit. If alpha equal to 0, then from 1, this is obvious. Okay? It's trivial or obvious. Now, if alpha not equal to 0, then alpha inverse exists because R is a field under addition and multiplication. So inverse element exists. So alpha inverse exists. Now alpha x x equal to 1x equal to alpha inverse alpha x now I think this is the last property, the last axiom, 10th axiom. Okay. Since this is theta given, so something into theta equal to theta, use this portion. Okay, hence this hold. Clear? Any problems up to second part? Okay. So now third, that is minus 1x x plus minus 1x. So we know 1x equal to x. This is the, I think it is axiom number 6th or 5th, I forgot, is mentioned it. So I write x is equal to 1 into x minus 1x. So I use this proper axiom c1 plus c2x equal to c1x plus c2x. One plus minus 1, this is 0 into x, so this is theta. Hence, x plus minus 1x equal to theta. Therefore, minus 1x is a inverse element of x, and I denote the inverse element of x by minus x. Hence, minus 1x equal to minus x. Here, reflection. Third line is the third line. Third line means this. From what? I think third line means which one? Can I repeat theorem? Can I repeat this proof again? Okay. Okay, please wait. X plus minus 1x. Okay. Since V is a vector space, so I think axiom number 5th or 6th, I mentioned this axiom x is equal to 1 into x. Okay. So I write x equal to 1x and minus 1 minus 1 x. So again we know C1, C2, I think this axiom number 8th or 7th is mentioned this thing here. C1x, C2x, where C1, C2 belonging to R, x belonging to V. So 1 and minus 1, 1 is a C1 here and minus 1 C2, and x belonging to V. Then from these axioms, I write 1 plus minus 1 x, and this is 1 minus 1 x. This is 0 into x, and I wrote in this theorem part 1, we see that 0 into x is nothing but a theta. Okay? For now. So x plus minus 1 x equal to theta. Clear or no? And we know the existence of inverse element. We know there exists minus x. For all x, there exists minus x such that x plus minus x equal to theta. Now comparing these two, we write minus x is equal to minus 1 into x. Hence proved. Clear? Thank you. Next, here theta, that is null element, is unique. Suppose theta is not unique. Assume there exist two null elements, theta 1 and theta 2. Then x plus theta 1 equal to x for all x belonging to V, and x plus theta 2 equal to x for all x belonging to V. Clear? Okay. Now take x is equal to theta 2 and use 1. Using 1, we get theta 2 plus theta 1 equal to theta 2. Using commutative property, we write theta 1 plus theta 2 equal to theta 2. Use commutative property. Okay. Denote this 3. This is 2. Now put or take x is equal to theta 1 and using 2, we get theta 1 plus theta 2 equal to theta 1, denote 4. Now from 3 and 4, we get theta 1 equal to theta 2. Hence, theta is unique. Okay. And again, prove that minus 6 is unique. This is your homework. I give some assignment before ending the class. In each of the following find precisely which axioms in the definition of a vector space are violated. Take V equal to R square x1, x2, define vector addition y1, y2, x1 plus y1, 0, comma, lambda, I think I write it, to x2 plus 1, alpha x1, x2, alpha x1, 0, x1, x2, y1, y2, x1, y1, x2, y2, alpha x1, x2, alpha x1, 2 alpha x2. So we define vector addition, scalar multiplication in defined way. So these two are the examples, and your job is find out which actions violated. These two cases, I give two more examples. See, x1, x2 plus y1, y2. So these are the 4 cases, and your job is find out which axiom or axioms are violated and prove this theorem. The inverse, additive inverse, is unique, and submit this assignment 5th February, on and before 5th February. Okay, so I want to close the class today, and we will join next coming Thursday. Okay, thank you. And if you have any problem, please, I wait 10 minutes, 5 to 10 minutes. If you have a problem, please ask me. And this is my mail ID. Dotto Ganesh 78 @gmail.com. So please send the assignment or mail the assignment to this ID. So if you have any problem, first line, which this minus x is unique, this one. Mail me. Okay. Dotto Ganesh 78 @gmail.com. Now, okay, I will send. If you have any queries, please tell me. I am waiting. Thank you. Theorem 1. Which theorem can you write something? I forgot. Theorem 1 means which? Just write something. That is, okay, so please repeat theorem 1.1. Okay. Okay. I got it. So, can you see this? I think it. 0 0 into x equal to alpha theta equal to theta. Now, I first prove this part. Alpha equal 0 into x equal to theta. Okay? So, 0 into x means what? I write 0 as 0 plus 0 into x. So, this is equal to 0 into x. 0 into x. I use axiom number maybe 8. C1 plus C2 x equal to C1 x C2 x, where C1 C2 belonging to R and x belonging to V. Here 0 and 0 both belonging to R, so I write this as 0 into x plus 0 into x. Clear? Okay. Now we know if theta is a null element, then for any element x belonging to V, then x plus theta equal to x. Now compare, this is 2 and this is 1. Compare 1 and 2, then we get 0 into x equal to theta. Got it? Okay. And the next part, that is alpha theta equal to theta. So we write alpha equal to theta plus theta. Why? We know for all x, can you see this? X plus theta equal to x, where theta is a null element, and x for all x belonging to V. So we can take x is equal to theta, then theta plus theta equal to theta. So I write this theta equal to theta plus theta. Now use these axioms. Cx plus y equal to cx plus cy, where xy belonging to V, c belonging to R. Then alpha theta plus alpha theta. Okay, use this. Now again compare this with this x plus theta equal to x. Then you see that alpha theta equal to theta. Clear? Please, if you have a doubt, please tell me. I think, is it clear? Shrutika, clear? Shrutika, clear? Yes or no? Please tell me. Shrutika. Okay. Any problem? Any doubt? Please tell me. If you have a still any problem, tell me. Last part. Last part. Okay. 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 So I think last part means this part. Okay. Alpha theta equal to theta. This portion. Yes and no. You want to. So I write alpha theta equal to alpha theta plus theta. Clear? Okay. Why I write this theta plus theta? Theta equal to theta plus theta because we know for all x there exists theta from axiom 4, I think, x plus theta equal to x for all x belonging to V. So since theta belonging to V, so we can take x is equal to theta. So we write theta plus theta equal to theta. Okay? Okay. So now we know from axiom 8 or 9, that is C, where C is a scalar, Cx plus y equal to Cx plus Cy for all C belonging to R, x, y belonging to V. So now alpha is your C, okay? And theta x, y. So alpha theta, from this axiom we write alpha theta. So alpha theta equal to alpha theta plus alpha theta. I denote this by 1. Again, we know for all x there exists theta, x plus theta equal to x for all x belonging to V. Now comparing